die die Amazon Web Services Cloud.
Thank you for all coming along. So I apologise if I'll apologise up front because this is not my usual talking topic. It's not something, but nonetheless, I'm standing in for one of my colleagues this afternoon who couldn't make it. So what I want to do is I just want to take you for a bit of a tour through some of the interesting technologies that we've built in the cloud that help do smart city things. But I really want to preface it from the point of view of talking about the smart city things first, right? I want to talk about the smart city things that we help, and then talk about the technology as a secondary thing, right? Because I think, it's important to understand how the cloud enables all of that stuff, and that's important. It's also important to understand why we're doing this in the first place. So, oh dear, I've got animated transitions. We're going to see how this goes. Anyway, so Dr. John Snow was the guy who actually figured out that cholera was getting spread by water wells in London from a couple of hundred years ago. So 1854, in fact. So he was the guy who actually figured out that disease is spread by microbes, and that the microbes were living in the water wells. And he did this by essentially plotting on a map where the disease infections were happening, where the diseased and sick people were turning up from. And then he just started looking at other things on the map, and he started plotting that around where the water wells were, right? And it was an interesting thing where he took essentially some geospatial data and mashed it up and looked at how his city was getting sick, right? And he did this in a methodical way. It's an interesting insight that he drew from data, right? And so it sort of sets it should give you an idea about what kind of things we should be, this is how we should be running our cities, right? We hopefully want to be able to do what this guy did. Was he was able to stop death in the city. And the way he stopped the death was that he went and convinced the city authorities to shut down a couple of the water wells. And then cholera, the cholera infection rate slowed down, and people actually got better or at least stopped dying as fast as they previously were, or in the same rate, right? So there was less death and more living, and that's always a good thing. Nowadays, we have different techniques for doing that. If you were here earlier today, you might have seen my eye chart of all of the AWS services that we have in the cloud, and we'll get to those in a minute. We'll get to those in due time, but essentially the point here is that we've now got slightly better techniques than just drawing dots on a map and finding out where people are dying. And in fact, today it's less about trying to stop people short-term dying, although that is important still. It's more about actually seeing how long we can keep them alive for. Can we keep them alive a bit longer? Can we keep them healthier a bit longer? And those are much more important things, right? Germany's a country where you guys have got a demographic spike. There's a lot of people born post-1945, and they're all starting to retire now, right? And this is a common problem in the Western world. So demographic spikes are things that we have to deal with, using data about our cities intelligently to actually try and do some analytics and try and predict where people's health is going, trying to predict the way that our cities are going to grow. It's really important. So this is why we do it. You can obviously see the population centers in Germany here on this map. The red areas, this is basically forecast population drop. So these are the areas where the population is expected to drop over the next 25 or 30 years. Between now and 2030 actually. So over the next 14 years, we're expecting the population to drop in these red areas. The blue areas, we're expecting the population to increase. I don't think you'll be too shocked. The cities are getting bigger. The countryside is getting depopulated. And so actually we need to actually, this is another data point, but we need to be planning around this, right? So we've got, so let's talk, this is really where we start talking about this idea of a smart city. And this is where we take data from our city, from instruments around our city, And we try to actually use that to improve people's lives. That's the mission. We've also got another thing that we add to it at Amazon, which is that we think that a smart city is one that's sustainable, both from an economic and an environmental point of view. So when we build new regions for our data centers, new regions of data centers, clusters of data centers around the world now, we're also building big electricity generation grids like solar farms and wind farms. And we're doing these things in order to make sure that we're both economically sustainable, because that helps us on our costs by keeping the cost of electricity as low as we can make it and bring it within our control, but also it's an environmental strategy. We've got a desire to get pretty much every megawatt that we use around the world to be a green and renewable megawatt in terms of the way we do stuff. And we think everybody should be doing the same thing as well, right? I don't think anybody in this room is going to disagree with me. So this is really the goal. Some things about cities are not smart. Somebody tweeted this last night. A guy on Twitter that I follow, I think this is really cool. There's life with electric cars. There's life without electric cars. Right? Hoping that electric cars are going to come and solve our city problems is not really the right thing. Right? The electric car is not going to solve our problem. I often face this in my job when I'm dealing with scientific computing problems. For many, many years, everybody's just sort of assumed that the Intel chip is going to get faster. And so that hid a variety of sins. It totally covered up a whole pile of really bad programming habits, because it meant that people could write crap code. But it'd get a little bit faster all the time because Intel was making the CPUs faster. The actual way to solve this problem, the actual way to make this stuff better, is actually interesting and intelligent insights from the data. And that's what we have to do. So we have to, in my scientific computing customers' case, they need to be writing better algorithms to be able to exploit the code, the hardware that they've got. In cities, we need to not leave it up to electric cars or some piece of technology like that to solve it for us. It's the analysis that we're going to do that's going to help us. So I live in this city. I live in London. When I'm not flying around. London is a hugely fast-growing city. There is actually, there's 9 new residents every hour. And I'm not sure what the ratio is between immigration and birth, but both of those are good things. I'm an immigrant, so this is, I think that's a great thing. So it's a fast-growing city. There's a lot of people turning up. Some areas of the country, like in the map of Germany I showed you earlier, some areas of the country the population's actually lowering, right? And with a lowering population or a shift in demographics, you may not need as many schools. You may need more hospitals. Being able to interpret this data intelligently is actually going to help us a lot. So we do a lot of work with London. We do a lot of work with Transport for London. So these guys are interesting. They've got so Transport for London is, I think if any of you have been to the UK and you've gone to London, TfL are the guys who are responsible for the tube, right? So you get I think you get your Oyster card, you tap onto the tube, right? And so TfL are responsible for the tube, but they have responsibility for all of the footpaths, the sidewalks, the roads, buses, trams, overground railway, underground railway, and I think and they regulate the taxis, and they're responsible for the bikes, for the bike rental system as well. So they have a truckload of data that they're actually sourcing from all of these operations. Now, a couple of years ago, they wanted to come up with an application that would help Londoners get around London more efficiently. Right? That was their task. Their objective was to try and figure out how to get Londoners moving more efficiently. If you go to London and you look at the tube map, it's enormously complex, right? Because it is a really, really sophisticated metro system. If you look at the bus map, it's crazy, right? I remember when I first moved to London, I looked at the bus map, I couldn't understand it. There's way too many buses. And the times of the day that they operate or don't operate, and on Sundays they take a different route over here, and on some other days they don't run after 6 p.m. or before 4 p.m. How could you possibly ever understand all of that? So they had this idea that they would write this amazing app that would help people get around and, essentially get better utilization of all of these services. And then they actually figured out that that was actually going to cost them a lot of money to write the app. And they weren't exactly sure that they could write the best app. And so what they actually did instead, and I think this is fantastic, this is a brave step for them. They actually open sourced all of the data that they have. Right, and they've now got a little bit more bold about this over time. But their first act was actually to release all of the data for all of the timetabling and all of the frequencies of the trains, where the trains were from minute to minute, and they put it all behind an API that they designed and published the data. Right, and then they let everybody else come and build the apps, which I think is great. Actually, it is a really good thing. So they just did a talk recently where they put this slide up. And they said that there's now 1,000 people, according to Deloitte, who did a study for them, there's now 1,000 people in London who are employed writing apps that are using all of the TfL data to give people, great advice for travelling and stuff. There's an app that I've got on my phone. Every Londoner lives by this app, City Mapper, right? Actually, there's about 20 different apps. Right, and indeed it stands to reason there's about 1,000 different people employed in London building these apps. But what's really cool is that, so these 1,000 people, this entire industry of all of the startups is generating tens of millions of pounds of economic activity in the city every year. Right, it is a real poster child for using open data in this way. It probably costs TfL something like £500,000 or £1 million a year for all of their activities in the web, pushing all of this data out. That's just a guess, but it's something like that, right? And in return, they get about 50 million quid worth of economic return out of that, or maybe even a bit more, right? So they really are a poster child for. They really are a poster child for using that data intelligently. Some of the other stuff that so they've actually they've moved on now, and they're now starting to release other data sets that they collect. So when you walk into the tube station in London, when you walk into any of our tube stations, you go underground and you'll notice that you don't have 3G anymore. Right? As soon as you go too far underground, you lose your cell phone reception, right? Because those tube tunnels are really, really deep. So what TfL did is they did a deal with the telecommunications companies, and they put Wi-Fi on all the train platforms and on the escalators. And what they do now is they track your MAC address on your phone when you come in. So when you come into the tube station and your phone connects to the Wi-Fi hotspot at the top of the escalators, your phone connects to it, and they record that as an incident, right? Okay, so he's at the top of the escalator. By the time you get to the bottom of the escalator, your phone's roaming over to another hotspot. And so they know how long it takes you to get from the top of the escalator to the bottom. And so they measure that for an entire crowd. And so they actually now know how long it takes people to get from the top of the escalators to the bottom. They can count how many people are walking down the escalators, how many are standing while the escalator moves for them. When you get to the bottom of the escalator and you get to the platform, they've also got more Wi-Fi hotspots down there, and they measure how long you stand around on the platform waiting to get onto a train. How many trains go past before you hop on the train, because that'll tell them how crowded the platform is. They measure the train's weight, so TfL actually has they actually have data on the weight of every carriage. They have weight sensors in every carriage, and so they can work out approximately how many people are on the carriage at any one time. So they're measuring tons of things. But again, instead, and some of this stuff they've been able to make use of internally, and they actually do make use of a lot of that data in order to predict how many trains they need to use each day, right? So how many, what should be the frequency of the trains on each of the lines? How much congestion is there? Should they have two escalators going down and one going up, or should they reverse that flow? What time of the day should they reverse that flow? What's the optimum one for doing that? So they're starting to get a lot of data on this, and they use that data internally to make their operations more efficient, right? And so and they're doing all of this stuff typically with resources inside AWS, because they can spin up analytical tools really quickly. So they're now actually starting to get more excited about open data, and they've opened up a few more data sets. So They've got an anonymized version of the data set for the Oyster card taps. So when you tap onto the train, they know that this is my card. Actually, they don't know that this is my card. They just know that it's a card that's got 20 or 30 quid's worth of credit on it. I can register it if I want to, but I don't have to. But they know that when I tap onto the train, I tapped in here, I tapped out at the other end. And so they've actually now got an anonymized version of that data set that they actually make available. So if you want to actually look at how Londoners as a mass move around the city every day, you can get a copy of this data set and observe that, right? And you can do something with it. So the reason they first generated that data set actually was because one of my customers, the research customer, wanted to actually check. It was interesting comparison to the cholera example earlier. What this researcher was trying to do was they wanted to look at the spread of infectious diseases across London based on data coming from the health department. And they wanted to see if that had some correlation with the tube system, to see if they could actually identify whether there were some tube stations that were hotspots for generating or propagating diseases, right? And so it's an interesting approach to the problem. So that research is still going, but it gives you the idea of the kind of things you can do with the data. So they're releasing traffic signal data as well, and then tram data. So same thing. These are all different bits of parameters about all these different modes of transport. The crowding data is what I was speaking about earlier, the Wi-Fi hotspot stuff, right? So they anonymise it. You can't tell that there's any one single person in there, with the MAC address. You're not going to be able to tell that it's Brendan Bouffler getting on the tube here and getting out there. So it's anonymised, but it's certainly sufficient to be able to start to do some interesting studies. You could use that data to figure out where Londoners were going most of the time. If you were, something really trivial and banal, if you were, you finish your PhD, right, and you discover that, a PhD in archaeology isn't going to do you so good, so you're going to open up a sandwich shop instead. You could get this data and have a look and figure out where your sandwich shop would be best located, right? Hopefully that won't happen to you when you finish your PhDs in this room. So, anyway, so you get the idea. So there's a lot of stuff that can be done with this. There's a lot of stuff that can be done with open data in the civic space. And so that even goes down to, judiciously locating Wi-Fi sensors in stores or on the street. There's more than one use for all these kinds of things. I was actually one of the researchers that I've been collaborating with recently, a researcher that works for the World Bank. He actually uses. They use data that they have an arrangement with a cell phone company in Tanzania, in Africa. And what they do is they actually take the GPS, the anonymised data set from the cell phone company for the GPS location of all of the telephone handsets on a minute-by-minute basis. And between that and satellite photography of the Earth that they're getting from things like the Sentinel satellites and others, what they're able to actually do is they're building a mapping capability for developing world cities that have never been mapped before. And the reason the World Bank is interested in this is because when they actually go and invest, by loaning some money to a country, to a developing country, and they give them some money, or they loan them some money to build a hospital, well, typically the decision-making process goes like this. I'm going to borrow this money to build a hospital. That bit of land over there looks empty. I'll put a hospital there. Well, the problem is that bit of land may actually be in a floodplain. Or, it may be in a fire, a bushfire, forest fire zone, right? That's not where you want your hospital to be when you have a flood or a forest fire and you've got casualties to treat. You don't want your hospital to be just as flooded and whatever as everything else. But in places like Germany or the UK or Australia, when we want to go and build critical infrastructure like that, we go and consult our central mapping authorities. In places like Tanzania, they don't have those. Those are very expensive things to have cartographers out running across the terrain all the time looking at, building maps of your cities and your country, right? Especially when all the roads keep changing and pathways change so rapidly. So these guys are actually using smartphone location data, cell phone location data coming out of the cell phone towers. They can actually use some machine learning algorithms to spot people walking down. They can understand that this is somebody walking down a sidewalk versus somebody on on a motorcycle riding down the street. And so they're building these maps, and it's incredibly good. So we can take some of those same techniques and adapt them into our own cities. And so we can actually find out, for example, where people do walk rather than where we want them to walk. Right? Civic designers always have this problem. We also did the same thing with cycles as well. Anyway, I want to make a point here that these guys at the Open Knowledge Institute, they actually they track how many open data sets there are being used in the world, and they actually rate different countries on their open data participation rate. And unfortunately, Germany's score is not so good. So I want everybody here in this room to get busy doing some open data experiments, right? If you do come from a city or you come from a government, I'd encourage you to have a think about how you can actually enable economies to happen by opening some data up. So we have these 3 laws of opening data. This is what I call Jed's laws. Jed is my colleague that runs the open data program in the company. And it's really simple. Put the data somewhere, tell people what it is, and make sure it's there tomorrow, right? And then actually, Transport for London did a really good job of their open data sets, but it was very planned and meticulous, right? They did do a really good job of building APIs, but they could have put a CSV file or an Excel spreadsheet up, and that would be an open data. That'd be a valid bit of open data. If somebody wants your data in a different format, well, they'll do it. They'll change the format of that data themselves. Don't fuss too much. That's really the point behind this is don't fuss too much about thinking about what your data should look like. We have this saying inside Amazon where we talk about polishing cannonballs. While you're polishing your cannonball to make it as aerodynamic as possible, to make it go really, really fast, all that time while you're spending polishing your cannonball, somebody else is inventing laser beams, right? And that's going to be the weapon of the future, and your cannonball is going to be obsolete quickly. So don't fuss around, when it comes to things like open data, don't fuss around thinking about it too hard. Get it out there is actually an important thing to do. Anyway, I'll show you some examples of this in a minute. We think open data is particularly important. We map a lot of different services onto open data. At the most basic sense, this is the CSV file. This is your spreadsheet put into a public web server so that people can find it. And this is really Amazon S3, right? The world's biggest file store, pretty much. Just an enormous collection of web objects. The next layer of insight is where you start putting some of this stuff in a structured way and putting it into a database. But you may find that actually it's the people who want to consume your data that do that for you, right? And in Transport for London's case, there's a group who've decided that TfL's API is not useful to them. They don't think it's in the right format and doesn't give them the right data structures for writing code. So they went and wrote their own, and they've now offered that as a service. So if you're going to write an app to use TfL's data and you like their API better than TfL's, then you can just go and use theirs. And that's what you want to do. You want to have sort of increasing layers of people offering different insights and being willing to share that out. And then, of course, putting analytic stuff on the outside of it is actually, this is really the beauty of the cloud, right? One part of the cloud's advantage for open data is just being a dumping ground for enormous amounts of data sets, right? And it's sometimes hard to discern where the commonalities might be. But then all of a sudden somebody actually works out that overlapping a spatial data set with the list of where all of the garbage trucks are going might actually be able to give you some data on where the potholes are around your city, and that's an interesting insight. So, being able to just mesh data sets together like that is important in this space. The other thing that gets really helpful about the cloud, for these problems is you can spin up arbitrary sized analytic workloads in place. Right? You don't have to know in advance that you need an elastic MapReduce, that you need a MapReduce algorithm to apply to your code. It can be something that you wake up in the morning and think, I wonder if MapReduce would help me solve this problem. And you can do that experiment and find out if it works or not. And in keeping with the cloud, with the thing that underpins the cloud is that if that experiment fails, you should fail quickly and it should be cheap, right? We call it failing fast. So if you're gonna make mistakes, you want to make them quickly and you want to make them cheaply so you can try the next thing out straight after that, right? It shouldn't cost you too much money to make a mistake, and it shouldn't cost you too much time either. And you shouldn't be left with a legacy bit of hardware when you're done. So that's the ability to spin up arbitrary analytic workloads that you didn't plan is really, really key to being able to make something out of this data. Because you also, if you are going to be smart and make data open, you want to put it in a place where it's flexible for a lot of different people to come along and try different things, especially things that you didn't think of. So Landsat's an interesting use case. I think I mentioned this earlier today, that Landsat's a satellite data set that we inherit from, that we host on behalf of the USGS and NASA in the US. It's a very large data set. If you want to get access to this data set in the past, you needed to have a 0.5 petabyte of spare storage, and you had to know somebody at NASA to give you a feed. We removed that minor barrier to entry by putting it in the cloud and making it available for free, right? And we've had 1 billion hits on this data set in the first, I think it was 11 months when we first put it up there. We had 1 billion hits, which is outstanding. We've had dozens and dozens of companies building applications on top of it. And there's been, really some cool insight. Landsat's a multispectral. There's a multispectral images that you get back from Landsat. They're visual images of the Earth, right, taken from space, but they're multiple different wavelengths. And so, in the infrared, you can actually detect the vegetation in a scene, and so you can immediately pick out the trees and the grass. In the shortwave infrared, you can actually pick out the cities and the urban areas. They are the things that stick out. And they have a different color. There's a lot of different techniques like that. And then, you can apply machine learning algorithms to some of these things to actually start to pick up new features and understand new things about your cities, right? So that's a really important one. And I'll show you there's some interesting tech that goes on the back of this. So I think I already explained this part here. So one of the things that we do, and this is where I mentioned that I talk about some of the tech when it made sense. So when the Landsat data actually comes into the cloud, we unpack it in our feed coming from USGS, and we put it ultimately into S3 after we've processed it a bit. We don't do too much processing, but we just do a lot of unpacking and rearranging of the bits to make it easier for people to get in a web context. Ultimately, we then have it hit this thing called a special notification service. The label has fallen off on this slide. But an SNS is a notification and queuing service that we have inside the cloud that allows people to then subscribe to this. And it's like subscribing to a news feed or a Twitter feed, right? So if you imagine that, your Twitter app on your phone, I'm going to follow this guy over here, and when he tweets, I'm going to get notified on my phone that he's sent me a message, right? He's broadcasting these messages, but I'm going to get notified when he's written something. So you can actually get notified when scenes arrive from Landsat. And then you can just set up a filter very quickly to identify whether or not this scene is interesting to you. So now what you can do is you can say, well, I'm going to get notified when scenes are coming out of Landsat. I'm going to look for ones that are relevant to me because they're scenes of my city, right? I work for Munich. I work for the metropolitan city of Munich. I want to know when the scenes are turning up of Munich, and when they do, I want to run my algorithm over those scenes and count the number of. I want to count how much vegetation there is. Right. I want to count how much vegetation there is by measuring how much green there is in the infrared scene. Right, as a portion of the total area, and I also want to measure how much of the land use is industrial or mechanized, right? And I'm just going to I'm going to roll that up. I'm going to even roll it up into a Lambda function written in Python, right? And Lambda is our serverless computing architecture where you can just deploy a little bit of code into the cloud and have it run on an event. Well, this can be the thing that drives that event, that causes that bit of Lambda to run, does that analysis to see, you know, to count what the land usage is, and then you can just get a number out of that, store it in a file somewhere. And now what that means is that you've got a continuous feed of satellite images coming in and telling you what the land utilization in Munich is every year. You can see how much green space there is. You can measure the green space down on a, you know, city block basis. And you might use that to actually determine, you know, how much green space do most of the residents have access to. Now, obviously, it's going to swing backwards and forwards throughout the year because the leaves fall off the trees and, you know, it gets cold and whatever. But what you're looking for is too much construction that's causing too many parks to go away, and you want to have an early warning indicator that maybe this is not a good thing. This can actually help you make some judgments about how to plan your city. So that's a simple example. A slightly more interesting example are these guys. So these are some customers I've been working with recently. They make bicycle lights. So I've got these on my bike. I should show you a picture of my bike. Every cyclist is always proud of their bike. But they make these lights. So these lights have got an accelerometer in them, proximity detectors, and light sensors. And so what they've done is they've packed some pretty cool machine learning algorithms inside the lights. So when I'm actually cycling of a night time, or in fact, I put these on my bike of a daytime now as well. So when I'm cycling, the machine learning algorithm gets used to the way that I ride, right? I'm a slightly crazy rider, so it's got used to my crazy riding style now. But what it does know is that, you know, they've also taught the algorithms in these chips to understand what are interesting circumstances on the road where a cyclist might be in danger, right? And those interesting circumstances might be that I'm slowing down, so the accelerometer tells the light that I'm slowing down to maybe stop at a set of traffic lights, but the car behind me is not slowing down, right? So the lights are getting brighter in the LED, in the light sensors, or maybe the proximity detectors seeing approaching movement behind me. And then what it does is it actually blinks the light even faster, and blinks aperiodically to get the driver's attention, right? So it's good life-saving stuff if you're a cyclist. That's pretty handy. The other interesting thing that they can do with these sensors is they pair it with an app on the phone, and that's what the cell phone is sitting there for. They've got it paired with an app on the phone. It's Bluetooth connected with low-power Bluetooth. It's pretty neat. I charge these lights about once a week, right? But the neat thing about the data that they're getting out of this is these guys are able to tell from the vibrational data they get from the accelerometer, they can tell what the road quality is like. And so, you know, if they were to put these sensors on, say, all of the rental bikes in the city, or if we were to put them on to some courier bikes, right, you can entirely foresee that you'd get daily updates on road quality across your city. It's cheaper to repair a pothole before it becomes a pothole. When it's just a bit of crappy road that's a little bit broken, it's pretty cheap to fix. It becomes more expensive when it becomes a full pothole, right? And even worse when it turns into this. In fact, you won't get any data from this at all with the cyclists because they won't ride there. But it's cheaper to fix a road when it's only a little bit damaged. And so they can actually get a lot of data out of the accelerometers in these lights, right? This is an incredibly insightful way of actually getting data around about a city. It involves amassing a lot of data, and then it involves applying a lot of analytics to it. So, you know, and this is where we get into discussions around the Internet of Things. So we've actually got we're able to service that. I mean, I think it's probably no mystery that we're doing an awful lot of IoT type work with hundreds or thousands of customers in this space. But we've actually got a service that's built for that, right? So we've actually built a service so that we can do point-to-point encryption of the data coming from the IoT device. So the IoT device registers with the cloud, gets an encryption key, point-to-point encryption, so all the data is always encrypted. It's authenticated. We have a device registry so that we can tell you what the devices are at. We have a thing called a shadow, which actually allows you to understand sort of the idea of what the state of the thing is. So if the thing happens to be a blinky light and it's got 4 or 5 different state variables inside it, we can actually have a shadow of what that representation of what that device's current state is in the cloud, so that you can actually write code that's running in the cloud that's making decisions on the basis of what the current state of the device is to push instructions out to it. And that can be sort of, there's a lot of different possible applications there. So it's this is a space that we can, that we can easily do some really interesting experiments in. One of the other really weird ones, and this is one that I helped with in Australia, again with the same research institute that I was talking about earlier today. But so what these guys have done is they're particularly interested in actually studying, and remember, we're talking about what is really a smart city. We're talking about, its human well-being. What these guys are doing is they're actually using Twitter. They're using a Twitter feed. They take a thing called the Deca hose. So it's basically 10% of the full Twitter fire hose, right? If you get hit with all of the tweets that are coming out around the world, that's referred to as the fire hose. So they take 10% of the hose. They run language characterization, natural language processing on those tweets to see if they can identify any emotional content. What they're looking for is to see if a human who's doing the tweet is trying to express some emotion, whether it's anger or fear or sadness or whatever. And then in the aggregate, they're measuring this for different geographical areas to see, looking at where the tweets are coming from. What they're actually looking for, these guys are doing research into human depression, right? Mental illnesses associated with depression. And what they want to understand is when there's nationally or internationally significant events reported in the news, how significant an impact does that have on the psyche of a city or a country or the world? And how long does that last for? So again, they apply some analytics to this, and they can actually tell that if a terrorist incident in a city occurs, they're interested in understanding how quickly do they see anger, despair, sadness around the rest of the world. How far away do you need to be, to be somewhat isolated from that bad news? And if you are nearby and you're affected by that bad news, how long does that bad news affect you for before you start to get better? And they can do this at a citywide basis. They've been discussing with one of the telephone counselling services, about, being able to use that as a predictive capability so that, if something bad does happen in the world, they can put extra telephone counsellors on, extra social workers on to be able to react to it in advance, right? So this is another really odd use of technology to come up with some insights. And if you talk to a lot of the practitioners in these spaces that have been building smart city technologies over the last 10 years, right? A lot of the stuff that they've been doing is taking pictures of the Earth with, say, a satellite and selling pixels, right? And selling people pretty pictures of their city. Right, well, that's interesting, but the really interesting stuff is where you actually do some analysis and you make an insight from that data. And that's actually really where we need to get to, which is, again, gets back to why it's important to be able to do analyses you hadn't thought of before, and to be able to spin things up quickly, make a few mistakes, and experiment with different types of compute workloads. So, again, we think this is really important. So, we do this with a whole pile of different services in the cloud. If you've never... Everybody here familiar with AWS? By a show of hands? I think most people are. So this is a bit of an eye chart, but the essential elements of this eye chart, right, behind all of these icons are a whole pile of different services, different instance types, different computing platforms, and so forth. The point of this eye chart is actually to indicate there's a lot of stuff out there that you will probably never use. It's there in case you need it. It serves the need of more than 1 million different customers. And because we've got more than 1 million different customers, every single one of them has got a different workload, right? No two workloads are the same. And so we keep building new services to be able to service new different customer types. So that sort of, this is sort of like a Precambrian explosion of species of workloads that you might want to pursue. It's there, right? But most of it is just simple stuff, it's simple building blocks that you're putting together. Server, storage, and network is really the underpinnings of all of it. But there's a lot of stuff in here that basically allows you to do really, really complex workloads really quickly. So spinning up a MapReduce cluster, right, a Hadoop cluster, takes a few minutes because, well, we did it once and we worked out how to automate that. And we've now automated it so completely you can just hit a button and have a MapReduce cluster really quickly. Virtually everything that you build in the cloud, you should, our best practice that we keep trying to teach everybody is that when you build it once, you should write down how you did it and turn it into a script so that you never, ever have to do it again. The next time you need it, you just hit a button and run that script again, right? And this is a continuous best practice, right? It means that you can build up quite complex things like this. This is that Twitter analysis, the Twitter emotional analysis. All of the tweets come in here. They hit a thing called Kinesis. Kinesis is our very, very high volume rate streaming messaging service, right? And then Kinesis, we can actually tell it to split the stream into different components and spit the output into a really large array of EC2 instances. And what it means is that as the tweets get greater in volume, right, different times of the day will have different volumes of Twitter activity. When a tweet storm breaks out because something big and important happens in the world and everybody's tweeting each other about Brad and Angelina, about something important instead, and when they're sending out all these millions and millions of tweets per hour, it can actually expand the number of compute things that are capable of consuming that data, right? And so that's what happens here. So, you can build quite complex workloads. And again, you build it once and you don't ever come back and do it again. I think I want to talk about Lambda, which is a particularly interesting one. So Lambda's this idea that we had, which is that spinning up workloads in the cloud. Like that last example showed you, you can multiply the number of servers that you have servicing your needs, right? But that's good, but it means that you're still managing a server fleet. But one of the things that we think is most interesting to IoT, and in particular in this smart city space, is when you're not going to know when you're going to receive sensor data. Right? You can probably guess some of the big trends. You're going to have a lot of cars going over traffic light sensors, between 7 and 9 in the morning, right? But you're still not going to know when they're all going to arrive and when it's going to start and stop. So if you've got sensor data coming from IoT sensors or from intelligent garbage bins or data coming from space, from satellites that are taking pictures of your city, and you don't know when the satellites are going to pass over your city to take those pictures, what you really want to do is you want to have a reactive capability. So Lambda was all about that. So what Lambda does, Lambda is where you can take a fragment of code and put it into the cloud, and it runs when it's provoked to run. So when an event occurs. And the event could be that somebody just pokes a web URL that is the URL for that routine and causes it to run. An event could be a file gets dropped into an S3 storage bucket. An event could be a message in our messaging system coming from the Sentinel or the Landsat satellite feed, and that causes a bit of code to run. But the neat thing is you don't have to wait for a computer to get spun up, like for a server instance to come up. It actually just runs this fragment of code straight away. All of the orchestration is done by us. And so an example I was talking about earlier, a genomics example, one of our customers has actually figured out that this Lambda backend is actually so flexible and actually so fast to respond with extra capacity that they're actually splitting up their genomics analysis workload jobs into 1 billion pieces and throwing 1 billion Lambda functions into the Lambda backend to see how fast it would work. Turns out that it just keeps growing and keeps processing them at an almost continuous rate. So when they doubled the amount of the number of jobs that they put in there, it actually just doubled the capacity. It didn't take any longer to run. They were pretty excited about that. So it's this really, really simple service where you can just throw routines. And so and the way that we calculate like people's usage is we calculate your usage based on how many hundreds of milliseconds you run for. So you could have a job. We give you the first 1 million Lambda requests every month for free. That's quite a lot. So you could have a job, for instance, that's receiving data coming from traffic sensors, right? And all of that data is coming in. It hits an S3 bucket or some other place, and it ultimately hits a Lambda function. And instead of then having instances come up and run batch jobs every hour or every 2 hours or something like that, you just have those. You're having that data processing continuously. So for something like an IoT environment, it's perfect, right? So its big advantage, of course, is you don't have to run infrastructure. You don't have to manage infrastructure in the back end, in the AWS back end, and it'll just continuously scale with whatever you need.
From the infrastructure point of view, from Amazon's point of view, what is actually running these Lambdas? Is a dedicated instance?
It's dedicated back end. Yeah, it's a good question. What's actually running all those Lambda functions? Lambda can either be, there's a few different languages that Lambda can be written in. Lambda functions can be written in Java, Python, or Node.js, right? These are Linux instances in the back end. I can't tell you all of the details because I actually don't know what all of the details are. We tend to actually try to get people to focus on the use case rather than what the back end infrastructure is, because it'll often change, right? And we like the ability to be able to change that stuff. If you're not trying to optimize, for what's behind the curtain, and you just focus on optimizing your code for its workload, then we can optimize the back end behind the curtain as we go along. One day it might be running on a CPU that you've never heard of before, right? I'm not saying it is, but we could do something like that if we thought we could deliver something faster and better, right? And it sort of abstracts things. It's just a great layer of abstraction. But in the back end, it's almost certainly a bunch of Linux boxes, Linux instances, and it scales fantastically because it's actually just using all of our infrastructure for auto scaling and just predicting in advance how much scaling needs to be done. But the cool thing is you don't have to write that logic. You don't have to be responsible for guessing. You just keep throwing Lambda functions in. And then, a Lambda function may just run for, 50 milliseconds, right? And that 50 milliseconds is enough time for you to check, your function might be, I'm waiting for 100 files to arrive from my garbage collection fleet. When my garbage trucks get back every morning, I want to see all of the garbage trucks logs when they come back to the depot. Automatically upload the logs. I want to see all of the garbage trucks logs because I want to look for data about the weight of the garbage truck, and I'm also interested in knowing how many miles or how many kilometres it drove, whatever the data is that you've instrumented in the truck. You could be interested only in analysing that fleet as a whole macroscopic fleet. And so what you could do is you could say, well, I'm not going to process these things as they come in. I'm going to process them one at a time. And when I've got a whole 100 of them, when the whole fleet's ready, then I can run a macro analysis of the entire fleet for the report that I have to run. Well, the first 99 instances of Lambda that are getting run might just be, how many files have I got? I got 99. Got 99, I've got 99, and just do nothing. And the 100th run, it says, okay, I've got the whole set now, I'm going to do my analysis and send the report to the garbage truck manager, right? And that these are pretty simple things to orchestrate. So I've got actually I know the video won't be on here because I'm not using my laptop. So anyway, look, so I'm hoping, because I'm coming to the end of time, the end of my time, I'm hoping I've given you a few ideas. I'm hoping I've given you a bit of an insight into how to, what kind of tools you can use to implement these things. But more than anything, I hope the theme that I really wanted to make sure that I got across was that, making a city smart is not just instrumenting it with tech. Making a city smart is actually the insights that you can draw from the data. And it's the insights that are really important. You know, whether you draw those insights by, great big scientific clusters doing analysis of something, or whether you draw those insights by just measuring things, counting things, and looking at trends over time, or mashing them onto another data set, like a geospatial data set, or going the one step further and maybe running machine learning algorithms so that you can predict. You can actually predict, you can make a forecast. If you've got enough data, you should be able to make a forecast about how much green space there's going to be in a neighbourhood this summer. So that when you get to the summer and you notice that there's not that amount of green space based on past trends, then maybe that indicates that people have been cutting down too many trees in that neighbourhood or doing too much construction or whatever. Or actually maybe you might even be able to use it to identify construction. I know of a company that's actually using the Earth observation data they get from some of the commercial satellite companies to actually identify construction areas so that they can actually see people clearing land and turning it into a construction site, and they can actually map that to see if they're allowed to do that. Do they have a permit for doing that? A great example I was told about a few weeks ago by a partner of ours in the UK is they've got an algorithm for counting caravans and tents. It can identify a caravan and a tent. And so what they do is they look at, they're interested in, say, if a local council has given 15 permits for camping in this camping ground, they've sold 15 permits. If they do a satellite overpass and they count 16 tents, they send the inspector out to go and collect the extra fee, right? If they only count 14 tents, they let it go. They move on. And given that you've only got maybe one or two inspectors and you want to use them wisely, that's a pretty cool thing to do, especially if you've got geographically dispersed camping areas. It's a pretty trivial example, but these are the kinds of things that should be possible. But what's most interesting from that is they're not delivering the council pictures of the Earth and telling them to go and count tents. They're counting the tents for them, giving them an insight. And so it's the insights that are the critical thing here, right? So we're actually now at that point where we can do these things. A few years ago, you had to have a lot of infrastructure and it was quite expensive to stand these kinds of things up. Now it's not. Putting bicycle light sensors that pair with people's cell phones and getting data out of that, that is now possible. The next thing, though, is to harvest insights out of that data, and that's what's most important. So anyway, thanks for coming along. Hope I've given you some ideas, things to think about, and I'd love to hear your ideas in return. So thank you for coming.